Good evening, everyone. Thank you for coming to the Alexandria Library's program tonight on resiliency in trees, based on or basically following the theme of our All Alexandria Reads program for the month of April and May, which is resilience. Our presenter tonight is Dr. Atticus Stovall, who works for NASA, and in his introduction and biography, Atticus Stovall earned his PhD in environmental sciences from the University of Virginia in 2017. A unifying theme of his work is using new technology to understand how the environment influences plants, especially trees. He is focused on measuring and monitoring global forest carbon and plant stress in 3D. Since 2021, he has worked as an assistant research professor at the University of Maryland, where he is mapping forests globally and using 3D models to understand how trees grow in different biodiverse environments worldwide. Now, tonight for our program, we are recording, and Atticus will present this in a webinar format. And he will be, Atticus will also, he will take questions in the Q&A. So if you have any questions, please post them in there and we will get to them as we can. And I want to thank everyone for coming tonight. And I'm going to go offline and mute and monitor any of the questions, and we'll jump in if there's a question that we feel like needs to be answered appropriately. So I'm going to let Atticus take it away now. Thank you again for coming.
Thank you for having me. Awesome. This is great to be here. So I'm going to hopefully successfully share my screen, and let's see if it works. 1 second. There we go. Okay, so why don't you just let me know, can you see the big screen? I can't see anything. So all right, I'm going to assume it's good to go. Yeah, first, I just want to say thanks for having me. This is really fun giving these types of talks because it's a good opportunity for me to kind of take a lot of the things that I care about and, some of the reasons why I got into science in the first place and studying trees, and really kind of like try to convey that type of stuff to you all. Hopefully, at the end of this, you'll see kind of some of the things that I think are really interesting about trees and plants, and how they can, really help us in moving forward into the next century with a lot of the uncertainty that we have kind of sitting before us. So I just want to start this talk. I start most of my talks with questions, and we're just going to be asking questions throughout the whole thing, because I think that's the best way to kind of approach all this science stuff. So the first thing I want to think about and consider is, why do we actually need to be resilient? So we hear this word thrown around a lot, and it's something we actually need to sit and think about realistically. What's the point? Why do we need to be resilient? So I'm going to show you a little video about why that's particularly relevant. And pardon me if the sound is on and really loud, because it probably will be. Okay, looks like I can mute it. So I wanted to open with one of the kind of the most classic diagrams that kind of shows how carbon dioxide has changed over the past, basically since 1950. This is called the keeling curve. So the keeling curve, when it came out, it became really clear that since the Industrial Revolution, there's a really dramatic increase in the concentration of carbon dioxide in the atmosphere. And even in the 1800s, physicists predicted that there would be consequences to that. Basically, just knowing how the atmosphere of the Earth works, they knew that there would be a rising in temperature in the Earth's temperature due to this increase in carbon dioxide. And I think, like, in terms of context to keep in mind with this is that right now we're at levels that are higher than they've been in 3 million years, just to give you some kind of perspective about where we're at. And so I wanted to just kind of briefly go through what I think is, an interesting kind of component of my story and how it relates to carbon dioxide concentrations. So the guy who just introduced me is my dad, Brack Stovall. So this is him when he was probably 6 or 7 or something, in 1960, at which point the carbon dioxide concentrations were around 315 parts per million. And you can see at the beginning of this keeling curve how it steadily rises, and we can skip ahead to around 1990, when I was a little younger than that. The carbon dioxide concentrations had increased to around 355 parts per million. And then when I was a teenager, around 385 parts per million. And then today, we can see, or actually since 1960, if we kind of put that in terms of percent rise, the current amount of carbon dioxide sits at around 32% higher than it was in 1960, and around 18% higher than it was in 1989. So right now we're at around 412.5 parts per million. I checked it today and updated it accordingly, just to make sure that I was up to date and everything. But the point of all this, and the reason why I mention this, is because it's good to kind of like step back for a minute and realize that in what seems like a pretty fast amount of time in our lifetime, there have been some really drastic increases in the amount of carbon dioxide in the atmosphere, and there are consequences to that. So with increasing warming comes a host of other things, like increasing frequency and intensity of wildfires. We see really high intensity coastal storms, and other inland storms, and pretty widespread drought as a result of this, among a ton of other ecological problems that come from the system of Earth increasing in temperature really more than is natural at this point in time. So this kind of leads us to this consideration, stepping back and thinking, all right, what can we actually do about this? Well, the first thing we can do and should do, first of all, is reduce fossil fuel emissions. And to actually do that, we need to know where carbon is actually stored. And so this is a big part of my job right now. And so I'm going to show you a little video that features this new sensor. It's a laser that's attached to the International Space Station. And the goal of it is to measure forests around the world and get an idea of how much carbon is actually held in those forests. Because it's one of these situations where if we don't actually know what we have, how are we going to make meaningful decisions about what to do, how to move forward into the future? And so what this laser does is it's shooting beams of light down into the forests of the world. The laser comes down, it hits the surface, and it bounces back with like a reflection, basically, of the energy of what it intercepted. And so that gives us like a picture of the structure of forests, and we can use that to figure out how much carbon is actually in those forests. And so some of this work was recently featured in a pretty cool documentary that I encourage you to go check out. You can find it online pretty easily. It was a NOVA program called Can We Cool the Planet? And it goes through a lot of really interesting strategies that we can use to reduce carbon dioxide in the atmosphere. And we were featured in there, as well as my supervisor, Lola Fatiembo, at Goddard. Um, and basically, we're using lasers uh, that are on the space station, as well as lasers on the ground and in the air, to really just map carbon in the most possible detail so that we can really get a handle on how much exists in the forests of Earth, so we can actually do something about it. And they made some pretty cool visuals to go along with that. These are the measurements of that JEDI mission. It's called JEDI, pronounced JEDI, but it's spelled GEDI, and that acronym is the Global Ecosystem Dynamics Investigation. If any scientists are hanging out and participating, they're probably aware of it. And a lot of people are very excited about this instrument because it's really changing the amount and quality of measurements we have of forests worldwide. And this is really, kind of like a next level instrument for the types of stuff that that I do on a daily basis. So you can see one more really nice visualization here, but basically here you can really see in 3D how the height kind of jumps out, the height of these forests worldwide, certain places, really jumping up quite high. And in some of the places where it's the absolute highest amount of carbon, say like the Pacific Northwest has an extremely high amount of carbon because of redwood trees and sequoias. And we're able to capture that. Finally, we're able to see that in 3D and translate that into the amount of carbon in forests worldwide. It's pretty amazing stuff that you can do with lasers. So we'll talk about lasers a little bit today. So while reducing these emissions, by measuring carbon, monitoring it, knowing what we have, really what we have to do in parallel with all of that is become adaptable. It's the way that we're, going to survive moving forward into the future. So the next question that we need to consider is, how can we actually be more resilient in this uncertain future that we have with climate change? And so the thing that I would suggest or say, and is really the overall focus of this talk, is for us to look to nature, because there are solutions that plants and trees and other beings, part of nature, that have really figured out how to survive long term in a sustainable way. So say we start with this tree here. This is a Great Basin Bristol cone pine. This tree can survive some of the most harsh conditions you could imagine. It's literally sitting on rocks. It seems improbable that this tree would survive in such a dry, rocky place on the top of a mountain. And not only that, is the oldest tree on Earth. They can live to be around 5,000 years old. And so we need to start to ask or consider, how can these individuals actually survive in these really extreme conditions? We're, as humans, going to have to figure out the same type of thing. Or we can look to something like redwood trees, which are the tallest trees on Earth. They can grow to be 120 meters tall, and they live for thousands of years as well. So how can they grow so effectively, but also live so long? These are, questions that kind of get us at ways that human beings can potentially become more resilient. Or this example, which I think is absolutely unbelievable, of a flower that seems like, a simple, unassuming white flower that was sprouted from 32,000-year-old seeds. So seeds of a plant 32,000 years ago were buried, and they survived 32,000 years until it was the right time to germinate and flower. This is, just an unbelievable ability of plants to, to survive in extreme conditions. We also have something like, for instance, all of us, I think, are well aware of the extensive wildfires that have happened all around the world. We've seen them in the US, on the West Coast, to Australia, the bushfires in Australia, the Amazon. And in a lot of these situations, one of the things we see is there's actually regeneration happening. So I'll give you a quick little video. I thought this was really interesting. After these bushland fires in Australia, you just see this regrowth and sprouting of things that, I mean, these were stumps, they were burned to a crisp, and the trees were able to survive and continue on. So I think these, are the types of things and strategies that we need to understand more about how plants function, so that we can try to do similar types of things when we're in situations of extreme conditions. So the next thing I want to, just briefly talk about is what is resilience? I keep throwing this term around. What does it actually mean? And I started digging into the literature and came across this paper from 1973 talking about ecological systems and stability and resilience. And one of the passages that really jumped out at me was this idea that resilience is a strategy that doesn't necessarily maximize efficiency or a particular reward, but it's one that allows persistence by maintaining flexibility above all else. I think this is really the factor here about resilience that we need to remember pretty consistently to really understand how best to adopt these kinds of strategies. It's about flexibility. It's not about being the most efficient or gaining this thing that you necessarily want. It's about being flexible so that when you experience something extreme, you have the ability to bounce back. So we can look and see what resilience actually looks like on, with like kind of a simple figure. The squiggly black line here is what you would consider to be like a stable state of an ecosystem, or you could even call it the stable state of like a city or a population or something like that, where, it just kind of oscillates up and down a little bit. But then when there's a disaster or some extreme event or something like that, something happens, and there are a range of different outcomes that we can expect. So if we follow the red line here, you'll see that we basically end up in a failure trajectory where we end up kind of disrupting the system so much that it doesn't really function like it used to. An alternative is this, really, you get this disruption and then you have the slow recovery where the system takes a long time to kind of come back to its original state, but it gets there. And then alternatively, you can bounce back really quickly, maybe, and you end up in the same kind of state as before. Or the best case scenario is you not only bounce back, but you build back better, and you build in a way that allows you to adapt to and absorb those extreme events more effectively, so that your system actually functions better than it did before. This is, basically A and B are what we would like. It would be great if that was the outcome of any sort of disaster that we encounter. So how do we actually put these ideas into practice? And another passage from that same paper that kind of came out at me was this idea that we need to devise systems that can absorb and accommodate future events in whatever unexpected form they take. And that, again, is, kind of in the same kind of idea of this. It's, it's about flexibility. We need to absorb these extreme events and find a way to actually persist despite how unfortunate they are. Anyway, so now that we've talked about resilience, I just want to go through what I thought was kind of an interesting thing to consider and just walk through, because I kind of asked myself this question, like, how did plants actually get to be so good at these survival strategies? How did plants get so clever? And so to answer this, we kind of need to go to the beginning, right? And if we go all the way back to the moment that plants started kind of creeping onto the land, they were, like most living organisms, they originated in the sea. And it was a pretty easy environment for them to handle, because they didn't need to worry about gravity or dealing with nutrients. They were bathed in their nutrients. They were bathed in the water that they needed. And they grew kind of slow, maybe because the carbon dioxide that they needed wasn't necessarily always in the water as high as they might want. But really, because of this, they started migrating, right? They started kind of moving to the shoreline, and some plants actually did attempt to kind of venture onto the land at the edge of the water. And once they got there, as you can imagine, compared to, the very luxurious kind of floating lifestyle of living in the sea, the land was harsh. It never had the water you needed, usually when you needed it. You had to deal with gravity, so you all of a sudden had to build some sort of structure, and you had to figure out a way to get nutrients. So all these things were kind of like, why did plants leave in the first place? This is pretty, amazing that this was even possible, because it almost made no sense. But one of the thoughts is that fungi were actually key for plants surviving on land. So plants actually, came out of the water and developed these relationships, these kind of relationships where the fungi and the plants traded different types of nutrients, where the plant might get carbon and give it to the fungi might get nutrients and send it to the plant. And so the fungi basically became the roots of the plant, because plants didn't need roots before. And so you can see kind of evidence of this, because really early plants end up having these like super underdeveloped, almost non-existent roots, but they somehow survived. And so the only logical explanation is that they had help. And one of the earliest examples of this is this liverwort plant, which you can see on the right. And if you zoom in with like an electron microscope and look deep into the cells of the plant, you can see fungi inside the cells of these plants, and they have these types of relationships. And so this combination and teamwork between these two organisms became so effective that they actually plunged the earth into an ice age. They were so effective at capturing carbon. The carbon came out of the atmosphere, and it decreased the temperature of the earth and went into an ice age, which I thought was like a pretty incredible fact that I found in the midst of putting this talk together. And then if we move forward in time, we can start thinking about trees, which is something that, of course, is near and dear to my heart. At 360 million years ago, that's around the time when the earliest trees first evolved. And these trees were nothing like anything you've seen before. If you look on the left, there's like kind of a drawing of what you might expect these trees to have looked like. They look like something out of Dr. Seuss. It's totally wild. But they were basically giant ferns. And the way they were most like ferns is they reproduced with spores. And like ferns, they could really only survive in moist and humid environments. So they were only successful in, like, a really narrow range of environments. But this first tree really paved the way for one of the most important and adaptable plants in Earth's history. And if we move forward in time even further, 280 million years ago, we can see the gymnosperms, or the rise of gymnosperms, beginning. And gymnosperm means naked seed. So it's a description of like what they do with their seeds. And most people know gymnosperms as conifers, or like trees with needly leaves. But it also includes ginkgo, which are actually the oldest surviving tree species, and something called cycads, which look like palm trees. They're interesting looking plants. But this new way of kind of having seeds with gymnosperms created the ability for these trees to survive in a lot more different types of environments. And it really changed the game as far as where trees could colonize and spread. So you can see in the earliest, the earliest thing that looked like a gymnosperm looked a lot like the Norfolk pine tree, which you can see on the left-hand side here. And then, basically after years and years of really creative forming and different survival strategies tried, these trees became able to survive in even drier and drier climates, survive in the face of extreme fire, and even grow to be some of the tallest and largest trees on Earth, like the redwood or sequoia trees. So depending on conditions, these trees could grow to be enormous or prosper in places that were seeming absurd to even survive in. And then at 100 million years ago, the very first flower bloomed. And this moment really changed everything in the evolutionary history of plants. So this picture here on the left is like a reconstruction of what they think the earliest known flower looked like. And from that moment on, something incredible happened. Because flowers came into existence, plants had a new way of drawing other species, animals, and all sorts of insects, pollinators, all these things, so that they could increase and really improve their genetic diversity. And so this allowed the angiosperms, as they're called, which are these flowering plants, to become incredibly genetically diverse and have a lot of different survival strategies that help these plants survive in basically almost every one of Earth's environments. It's really incredible what this type of diversity has kind of led to in terms of survival of plants. And we can also look around 92 million years ago, the earliest flowering tree, and they were enormous. They were 150 feet tall, 1 meter in diameter, like more than 3 feet in diameter. I mean, they're very large trees. And this particular one, there's a paper that came out really recently where they discovered this in Utah, a fossilized specimen of this flowering tree. And it lived on the coast of this inland sea that existed around the Midwest. So here was just another, another individual in this long list of plants that was, surviving and coming up with different survival strategies because of its flowering kind of approach to survival. And then we can move forward to basically one of the most amazing, I think, specimens of angiosperm or flowering tree, or the mountain ash, or the eucalyptus in Australia, which can grow to be more than 100 meters tall. They are almost as tall as redwoods, and they're flowering trees. So it's amazing that we've, come so far, and plants have really adapted in this kind of way over time. And really throughout this entire kind of time span, one thing has been consistent, is that basically the number of species of any particular group of plants ebbs and it flows, but consistently the genetic diversity overall increases dramatically. You can see in this nice little figure here that, you get increases and decreases of certain types of plants, but ultimately over time, we just have this rocketing up an increase of plant diversity. And now we have around 320,000 species of plants. And if you were to try to guess what proportion of that were angiosperms, I don't know if someone would throw out a number, but it's 300,000 of them. That means like a humongous percentage of that 320,000 species are flowering. So clearly it's extremely successful way of increasing diversity in the plant kingdom. So then we can also look at the genetic diversity of trees over time. And in another recent paper came out looking at the number of tree species on Earth, and they were finding that approximately 73,000 species of trees exist on Earth. And so they can kind of project what the number of species that should exist are. And so that means we have 9,000 species that we've yet to actually discover. So there's, I think in the world of science, we can sometimes feel like, oh, like everything's been discovered, but this is, we're still learning so much about nature. And this amount of diversity, really is the key factor that is allowing us to learn something about how to survive as human beings if we're taking these lessons of survival strategies from plants. So the key there is be flexible. And so if we just kind of review that really 450 million year history that we just went through, 450 million years ago, plants emerged from the sea. Trees came up around 360 million years, Gymnosperms 280, angiosperms 100 million years. All of this time, this is a lot of time to figure out things like learning lessons from different extreme environments. That's basically what evolution is. It's plants, in a way, learning lessons about what works and what doesn't work. And so it's now our opportunity to basically look at this tomb of knowledge from plants so that we can potentially start to understand what they're doing, and can they teach us something about how to survive, be more resilient in unexpected and difficult conditions. So for the rest of the talk, I'm going to go through what I think are some of the interesting ways, or a few of the interesting ways, that plants have learned to survive. And really the unifying theme for every single one of these lessons, you'll see it in every one of them, is it comes down to one word: adapt. So if we want to be able to not only survive, but prosper, be happy and healthy into the future, the key thing we have to do is adapt. So for our first lesson, we can consider how we might adapt how we get energy. So let's quickly just look and see what a plant survival strategy with this might look like. So here we have, I don't even know what this is growing. If anyone recognizes it, maybe put that in the Q&A. But we have these seedlings growing, and you can see that they follow the light. This is such an interesting example of how plants are really efficient. This is called phototropism. So it's basically the ability for plants to follow light. You can see how quickly and drastically they can adjust to a really dramatic shift in the light environment. What we can also see is that sometimes, instead of trying to find the light, plants are actually reducing the amount of light that they absorb into their leaves for protection. So this plant here, you can see, drops its leaves during the daytime so that it's shielding itself, reducing the amount of light that comes in. And it's a really efficient strategy that allows the leaf to keep from overheating, and it makes it more efficient really at all hours of the day. And so one of the things that we're doing in our research group is we're using lasers to understand the movement of leaves in these really complex forest environments. So what we do is we go out into the forest and we scan the forest environment with these lasers and create this virtual forest where we can then track the actual movement of the leaves in the forest canopy. We can see the angle of them, the direction they're pointing, whether they're in the sunlight or not. And so we have an idea of what the light environment is and what the leaves are doing. And we want to use that to understand why leaves move, basically. And so one of the interesting things we found is that the leaves in the forest do, similar to these other plants, do track the position of the sun. And they're also very sensitive, even more sensitive to the local light environment. So that basically means that if they're shaded overhead or the sun is directly on them, they'll adjust accordingly. Just like those two plants that you just saw, we're seeing that in a full forest canopy. And what this is doing is it's basically changing the way we actually think about forests, since we tend to assume leaves just kind of are there. They don't necessarily move much, and it doesn't even really matter. But as it turns out, the movement of leaves in this way can actually affect photosynthesis by as much as around 30% in some forests. So this is the type of thing that, if we don't really have a handle on it, has kind of implications for how we think about how these plants actually function. And now we've really kind of uncovered this thing that we think will help us maybe learn something about how to be more efficient in our own energy capture solutions. An example of that might be optimizing the position of solar panels, for instance. So, the next generation of solar panels aren't necessarily going to just be stationary. We're going to have solar panels like this, where all of them are moving regularly, optimizing and, catching the sun at the best possible time of day. And this, will allow us to have a more efficient form of energy capture. Another really fascinating way of kind of thinking about the efficiencies that we can, or I guess inspiration from plants that we can take that can improve our environment, are these super trees in Singapore. So they've created these 18 super trees, which are basically vertical gardens. They're covered in plants. They generate solar power. They have solar panels on them. They also act as air venting ducts and that allows them to filter the air and collect rainwater. So we have this extremely multi-purpose, beautiful architectural kind of urban architecture kind of thing that is also providing a lot of, I mean, basically almost the equivalent of like ecosystem services, but it's a, you know, totally urban architecture. So that was something I thought was really fascinating. I'd love to go there and check that out one day. It's pretty amazing. But the next thing that we're going to focus on is, again, you see this word, lesson 2, adapt how we live together. And I think there are some interesting lessons in nature that we can take from this. The first I'm going to show you that I think is really cool and has always fascinated me is this phenomenon you see on the left, which is called crown shyness. So it looks like you have, you know, cracks moving through the forest canopy. And for a long time, it was assumed that this kind of phenomenon was maybe from like trees swaying and like branches breaking off and stuff. But some new work using those same like 3D laser scans allowed us to kind of look at this in more detail and in 3 dimensions. And basically what's now clear is that trees are actually optimizing or able to kind of sense their surroundings, and they basically respect the space of their neighbors while living as close as possible. So and I think it's absolutely fascinating because you look at this picture on the right, and these trees are basically hugging, you know. I mean, they are as close as they can be while without actually touching. And what's really interesting is that this even applies in these really complex forests where it's hard to see with your eyes, but this 3D data has kind of shown us that, oh, it's like, all right, plants have found this really efficient way of cohabiting together in a forest. And it's not necessarily a competitive interaction. That's still, I will say, that's still kind of a up for debate thing. But a lot of people think like there maybe needs to be a different framing of what competition actually is in forests. It's still kind of an open question here. And so one of the things that we can, you know, do with that information is, well, we can consider the importance of these urban spaces and really understand how important it is that the vast majority of people are living in urban areas as we move forward into the future. The reason for that is purely, we can look at it from an efficiency perspective. So urban areas are 13% more efficient than rural areas and 30% more efficient than suburbs. That's a huge difference and could make, you know, basically make the difference in terms of emissions and climate and emissions goals. So the other thing with this that I wanted to mention really briefly is I heard this on the radio just yesterday about human well-being and per capita energy use. This was this paper covered on NPR. And the main kind of takeaway here is that in terms of if you're an American, you use 4 times what you actually need for a happy and healthy life. And obviously that is like very subjective in many ways. But in terms of what is considered to, you know, be happy and healthy, there are a lot more efficient ways to get to where we are right now. It's basically just saying you can be happy, but by using more efficient means. And so, you know, some of this here, this kind of wasteful per capita energy use can be addressed by rethinking how we actually live together. And if we kind of extend this into the kind of resource kind of realm of things, we can see how forests, they don't only assemble efficiently, they're willing to share resources so the entire forest prospers. So, in a recent book, which I'm sure a lot of you have come across, this book by Suzanne Simard, called Finding the Mother Tree, where she discusses this kind of idea where there's kind of a dominant tree in a forest, and it kind of actively shares its carbon and nutrients with other smaller trees to support their survival. And what's absolutely incredible to me about this is not like species dependent. This is across the board supporting the forest, and it will be across species. So the way that this happens, though, is like we talked about before, these mycorrhizal networks, which are like the fungal networks that are in the soil, are actually allowing these kinds of connections to take place and happen. And another book that I can't recommend enough is Entangled Life, by Merlin Sheldrake. Very cool book, really interesting, and just if I could tell every person here to go out and read that, just do it. But one of the really cool things in there is, it's basically taking a deep dive into that idea, and shows how, these complex networks kind of support the growth and survival of forests through creating a really complex system of interconnections. And so this idea is going to be especially relevant to the populations of people who will be most affected by climate change. So we first, like the highest priority is we need to actually consider the human population as a whole, not necessarily thinking of our own nations, but working together as humanity, just so humanity is able to prosper. And one of the, really key things and the reasons why this is important is because if you look at the nations that have prospered most from fossil fuels or benefited most from fossil fuels, they are not the same nations that will be dramatically affected by climate change. So there's going to need to be a consideration of humanity as a whole, and resources and support will need to be, distributed to vulnerable populations with climate change as it, gets worse, basically. All right, so moving to lesson 3, we're going to talk briefly about how we might adapt how we grow as a society. So the first thing here is use resources wisely. They aren't unlimited, and trees are the masters of adapting how they grow. So if you look at the rings of a tree, you can clearly see times of prosperity, times of hardship, and times where there's just no growth at all. And you see this in the oldest known tree, over 5,000 years of its life. It's not just growing full out regardless of what's available. That tree would just die. It dials it down and adjusts according to what's available. I also would encourage you to read this book, Tree Story, really interesting book that focuses a lot on the tree ring stuff, which is called dendrochronology. But in this is a really interesting story about how the oldest tree on Earth was actually cut down by a grad student. So yeah, got to watch out about that. But like trees, we must grow only when resources actually sustainably allow. And the strategy here is we have to take the long game, in terms of our societal growth, basing our decisions on, what we believe is coming in the future, making informed decisions. And trees, they do this slowly over time. They're adapting to the environment, expanding when it's possible to expand. And we have to do the same. We can't overexhaust resources and, create a more sustainable society just by using everything that's available to us. And this also reminds me again of this, little unsuspecting flower that sat for 32,000 years because it wasn't the right time to grow. So there's a lesson there, I think. And interestingly, trees, they actually take the efficiency one step further, and they'll adapt their growth based on time of day. And it's not what you think. So as it turns out, trees grow mostly at night. I'm sure most people here, including myself, probably would have assumed that trees grew the most when the sun is out. But again, if you think about the conditions in the like a summer night versus a summer's day, it becomes pretty clear why you might want to do your growing in the evening, because it's more pleasant. And I think we can, extend this analogy to if you ever, drive down the highway late at night, especially around DC, a lot of road work going on. And the reason for that is it's more efficient and it's safer for people working often to be out of the heat. So this is just another example of ways that we can kind of adopt these ideas. Another factor we have to consider are the rising seas with sea level rise and the extreme storms that come to the coast. And trees are already moving inland in response to this. And people will have to do the same. So you see this because of saltwater infiltration on the coast, that trees are backing off because they can't survive with the sea level actually rising. And one of the things that we're actually doing in our group is we're trying to understand why some of the most important coastal protections that we have, mangroves, are dying in some areas and not dying in others. And so we're doing that again with 3D lasers. And so here, this is a little fly through I made of data our team collected in the Everglades. This was a stand that did not survive and recover after Hurricane Irma came through and just basically decimated the landscape. But some stands totally did, come back. They were very resilient. So we want to understand why that is. And to extend that analogy to people and what we should do, we know where the seas are rising. We know where we're going to need to move and the likely places that people will congregate from the coast because the sea level is rising. And so coastal populations will also need to, they need to go somewhere. And so if we, build these more efficient urban communities, we can actually house displaced people in a more sustainable way. And then when we do rebuild, or we're building kind of the next generation of urban areas, we can consider the possibility of actually storing carbon when we do it. Something that I came across a couple years ago that I just did not realize is that people are actually trying to build like high rises made of wood. And one of the reasons, or the motivations for that is because you can capture carbon and hold it there, because there aren't really necessarily carbon emissions lost because the building is standing. Like this example here of this timber frame building in Norway that's 280 feet tall, 18 stories. This is pretty incredible. This is even possible. And you can also basically come up with a carbon footprint for how much it's storing. Like a 5-story building might be able to store around 400 pounds of carbon per square meter, which is around 3 times a mature forest is able to store. So there are a lot of options we have. And of course, like this is not, something we can, have everywhere. There are a lot of places where you wouldn't want to build a wooden building where there are fires or earthquakes, but there are plenty of places where you can, and it could be a potentially, beneficial way or useful way to reduce emissions in some countries. There you can see just kind of a look of the down the stairs. Pretty insane. All right, our fourth and final lesson, adapt our environment. I wanted to we're almost done. Thanks for hanging with me throughout this talk. It was really fun for me, but I wanted to just briefly take a second and think about how it feels when we walk into a forest. So you walk, you're walking in a field and then you enter a forest. Think, in your body what it actually feels like. As soon as you walk in, you notice there's a temperature change. It might feel a little bit more damp. The smell is like earthy, but it's not only from the dirt. Like the trees are actually emitting things called isoprenes, which actually affect human beings. These chemicals have actually been shown to reduce our blood pressure, and basically make us live longer by being close to and in forests. Something that you can read more about in this another really interesting book, The Heartbeat of Trees, and I strongly recommend that one as well. But what I'm focusing on here is why we actually feel that when we enter a forest. Well, it turns out that forests directly change their climate, kind of their environment, their internal environment, by just existing. So it's basically universal. Wherever a forest is, the climate's more moderate than the same place without a forest. Trees in forests directly affect their environment. It's a really interesting thing that we can feel when we go into a forest. And the other thing to keep in mind here is a lone tree, a single tree, is far more susceptible to extreme weather and is more likely to survive when it's actually protected by its neighbors. So if we consider the coming extreme temperatures and weather, we'll need to actually figure out ways to adapt our environment like trees do to make life more comfortable or more pleasant. We know it's going to be hotter, so we got to do something. And one very easy thing we can do is we can plant trees. There's a huge effort right now to plant trees globally. I would not suggest planting trees absolutely everywhere. There shouldn't be trees everywhere. There are plenty of places that do not need trees, but especially in like urban environments that were once covered in forests, those are very useful places to increase the amount of cover of trees. And planting needs to start basically. There's an old saying that's like the best time to plant a tree is like 40 years ago. So we need to get on it, basically. There was a really interesting National Geographic article recently that covered the DC area, and it was looking at the basically looking at the amount of heat in different areas of the city and showing really the dramatic difference in temperature that exists across the city between the forested area and the concrete area, which is around 16.5 degrees Celsius cooler, which is, Fahrenheit, which is a dramatic difference. And you feel it if, you live in this area, if, you're in the concrete, basically concrete jungle kind of area, and the Rock Creek Park, there's a huge difference on a summer's day, and kind of where you want to be. So the key here is there are more trees that are really needed across cities globally, especially since there tends to be a huge disparity in tree cover in less wealthy neighborhoods and neighborhoods with high proportions of people of color. This is going to be super important because there needs to be equity, basically, in tree cover as climate gets more extreme. People will need to be able to get out of that heat. And this is an easy way that we can do that. And so with respect to sea level rise, one of the easiest things we can do to protect us from coastal storms and flooding is to plant mangroves, or whatever, the appropriate kind of coastal plant actually is. This, like mangroves, for instance, can reduce wave height from storms by around 60%. They basically they're amazing for creating safer coastlines in the future. So any mangroves that have been deforested should be replanted and protected. And that's another thing that we're working on, again, with lasers, surprise, surprise. And so we're basically using this 3D data to understand why some trees survive, why others do not, and really understanding the resilience of this system, on top of all the measuring of carbon that we're doing. There's a lot more to learn about forests than just how much carbon they hold. And hopefully we can actually, learn some lessons of resilience along the way. So now that I've talked quite a bit, I just want to go back again to this kind of definition of resilience and think about kind of where we came from and where we're going. So the key here, again, is maintaining flexibility above all else. That's the most important thing moving forward, is we need to be flexible, we need to adapt. And recently, just like a couple weeks ago, the 6th climate assessment of the IPCC came out, and they were talking about mitigation of climate change, and nature-based solutions were a huge component of how we can actually achieve the climate goals that that we actually have put in place. So and then one of the other things that was a real big takeaway from this is reducing emissions and creating like more sustainable cities and more sustainable societies is actually really possible. The technology is there, but we don't necessarily have the investment we need to get it done. And the only real reason why it's not happening is, unfortunately, political will. So as individuals, we need to push that. We need to push that to make sure that something actually moves on this, because it's now that it needs to happen. And the other piece of this that was emphasized in that report is that there's a real need to listen, learn, and support Indigenous populations. These people will be incredibly vulnerable to the effects of climate change caused by industrial societies, but they also have the solutions that we need for the world to actually be more sustainable. So we need to rely on this deep knowledge that's a part of Indigenous cultures that they're already using. They're already using the lessons in resilience from nature that we're talking about here. And so there's a lot to learn there. So just to go through these one last time: adapt how we get energy, adapt how we live together, adapt how we grow, and adapt our environment. Really, the bottom line is, like plants, we must adapt. That's what we have to do. And so if we consider where we've been and all these milestones that I talked about before in terms of carbon dioxide and what they mean for the climate, we know there are ways to adapt to this changing climate and actually, make a difference in this. And, if we start kind of projecting forward, if I have to make that little keeling curve, I have to make it really small to actually fit it on the graph that shows where we're going in a worst case scenario or even a best case scenario. So in 2100, if we do nothing, the results will be catastrophic, but we have the solutions to avoid it. We just actually need to implement them. And in doing that, if we heed the lessons of resilience from the deep knowledge provided by trees and other plants, we as a species will be more fit to actually survive in the next century and all the centuries after that. So with that, I'll say thank you, and we can do questions.
Thank you, Atticus. I do have a couple of questions. The first question is from Kristen, and she's asking, how can a dead tree lumber store more carbon than living trees?
That's a great question. Yeah, so part of their calculation with those buildings is because they can build them like really tall and fit more wood per square meter. If this is with regard to building like timber framed high rises, that's basically how they make that work. Is and the thing is, like, no, we shouldn't like cut down all the forests and just like, build cities, obviously. But I think the key there is that we can, we can pack a lot of carbon into a small space, and that carbon isn't going to go anywhere until that building falls down, basically. So it's kind of, this is not a forever solution, nor is a forest. Forests and trees die. But it's almost like one of these adaptable solutions where you're able to, take into account, or the fact that human beings are going to want to have or actually need to have these urban areas in place so that we can live more efficiently. And if the buildings that we choose to build capture carbon, that's just kind of a plus. So, yeah.
Another question from Ashley, and this is very pertinent because we're experiencing very extreme conditions, extreme droughts, extreme weather conditions causing flooding. This has been happening. It seems to be our future. How are trees and plants going to be resilient to those types of extremes in the environment?
Yeah, well, I mean, that's a good point. And there's no guarantee that they'll just be happy and prosperous. Some of my other work, which I chose to exclude because it's very doom and gloom, maps millions of trees that have died in California because of drought. So at a certain point, trees are pushed beyond their limit. But the thing that's kind of interesting here is it all depends on kind of your frame of like your time span that you're considering. So if we, are looking in the span of 10 years, millions of trees, what we'll see as human beings is that millions of trees will die. And that will be, it's a really catastrophic event. But in the kind of grand scheme of things for the way forests function, is they kind of ebb and flow based on the places that are most suitable for them to survive. So if a place has extreme drought, maybe the forest will not come back there, but maybe a forest will creep into somewhere where it couldn't exist before. It's hard because inherent in all of this is a lot of movement and uncertainty about where forests are going, and how resilient they'll actually be when really pushed to their limit. But that's just something that we kind of have to see when it comes. And hopefully, I think there's so much evolutionary history kind of inherent in trees and other plants that there are like a lot of survival mechanisms built in there that hopefully will allow forests to be more widespread than they are right now. I think that that's very much a possibility, especially with all the like reforestation efforts that are happening now.
Well, I have a question related to that. Also, one of the viewers submitted a question about the extreme climate change and if whether that moves too quickly. And I was thinking about it in those lines. The big catastrophic event that occurred was when the dinosaurs were wiped out hundreds of millions of years ago. And what geological evidence do we have, or do you know of any that indicates how that geological catastrophe for the dinosaurs, it must have affected the forest at some point, and they did survive? Have we learned anything from that? I mean, that we can see in today's?
That's a good question. Yeah, I mean, my particular, my area of like expertise. I could, pontificate about like the answer to it, but I don't know. I don't know the actual answer, but I would say that, you know, one of the things that we know about that like period of time is basically, an asteroid or something hit the Earth, and the Earth's like light levels decreased really dramatically, which actually killed off a lot of plants. That was the thing that killed the dinosaurs more than an asteroid didn't just like incinerate them all, like, Armageddon or something. But more so, it was like all the food disappeared because it was like darkness, and plunged into this like the equivalent of like volcanic winter. I don't know what the asteroid terminology for that is, but yeah, but then again, like, trees and plants and, all these things survive because they have seeds, and they have the ability to go dormant and just wait around, like, that one seed for 32,000 years. So, maybe I don't know what the I don't know what the lesson is from that, but we'll have to get in touch with Bruce Willis for all Armageddon related questions.
And another question, someone has asked, have you written a book about this? And also, what was the first major tree species in North America?
Ooh, that's a good question. So, no, I haven't written a book about it. That would be fun. I read this talk about it, which was, basically just for fun. So maybe I should write the book. But yeah, I don't know the first major tree species in North America, partially because the continents, like, so trees have existed so long that there's been like geologic movement in the shapes of the continents, and like one reason why you might find like one species in like one place that's surprising is because you have continental drift, and basically like species could like evolve in parallel. It might have like split in some different directions and things like that. But the short answer is I have no idea what the first species was, but that's partially because North America didn't look like North America probably when trees first colonized. So yeah, it might, I mean, I guess you might say that earliest, I know the earliest flowering tree, which I put in there, but I'll look that up. I think it's a really good question. I'll see if I can figure it out.
Well, if you find out, I have the email addresses for everyone who's in the program.
Oh, sweet.
I will send it out, follow-ups for that. So
That sounds fun.
On that note, I think this is a good spot to end. We're well past 8. Thank you very much for your time tonight. I just want to give some final information to people. I want to appreciate that you came for our program tonight. This is part of our All Alexandria Reads programming. We have several more programs this week coming up. We have Learning for Laughs, Comedy for Kids. It's a program tomorrow, and 4:30 to 5:30. Then we have it's a virtual program, and we have the World Art Day. Take and make world art projects. That is actually, I believe, that is also a virtual program. And then we have Becoming Resilient When There Is Resistance, which is Saturday. And that is going to be at the Charles Beatley Central Library. It's from 1 to 3 p.m. And we will meet with the Alexandria's Poet Laureate, who teams up with Molly Rufus, winner of the Young Poets in the Community Award, to share a writing workshop on this year's All Alexandria Reads Themes of Resiliency. So make sure you put those on your calendar. And again, I want to thank you, Atticus, for coming tonight. And this was very, very fun and very informative. Let's see, I'm going to check and make sure we have, thank you, fascinating. Thank you, great talk. So
Thanks,
everyone, thank
everyone.
you so much for being here tonight. And I am going to, this program has been recorded and we will put it up on the library's website within the next week. So thank you again, everyone.
Thanks again. Happy almost Earth Day.